Hello and welcome to the wolfSSL live webinar supporting TPMs and embedded devices with wolfSSL engineer David Agarski. My name is Marcos and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box or you can raise your hand to be unmuted once we start the Q&A session, which is going to be following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you to follow us on Twitter at wolfSSL as well as our other socials. Also, feel free to email us at facts@wolfssl.com if you have any additional questions. And now I'm going to give a quick company overview before we start the technical presentation. wolfSSL was founded in 2004 by Todd Osko and Larry Stefanich when they realized there wasn't an open source, well-licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2022, most of which are engineers. This progress is, of course, supported by a strong partner network that we're proud of, which includes DDCI, STMicro, and RTI, for example. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and FIPS ready offering. MQTT up to the V5 specification, SSH v2, TPM 2.0 secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. That's all for me, so I'm going to hand it over to David now for the presentation.
Hi, everyone. Thanks for coming to this webinar. And today I'm going to talk about TPMs and using them in an embedded environment. Really quick, I wanted to mention that we also have some new products like Wolf Sentry and Intrusion Detection Prevention System, and this is basically an embeddable firewall. And then, although I'm not going to cover it, we did also add a bunch of new C# wrappers for wolfTPM, which makes it really handy to use the TPM on Windows. But a focus today is going to be on the embedded space, embedded targets, and how to adopt use of a TPM and why adopt use of a TPM. So first I wanted to talk about the TPM 2.0.
David, could you pause for a second? Someone submitted a question saying they see a black screen. Can anyone in the chat just confirm if you can see the presentation?
Wow, that's my bad. I had it paused. Man, that's embarrassing.
Okay, so
yeah, so we'll just go through these slides again real quick since everybody missed them. This is our products. This is our dual license, all that stuff. And then here, this is where I started. So yeah, I wanted to go over, and thank you, by the way, anonymous. So the TPM 2.0 specification, it started a long time ago, and it was really something that the big manufacturers like Intel and Microsoft and IBM, they came together and collaborated on as part of the Trusted Computing Group. And the idea was to standardize a way to protect keys, right? So a secure key store, also a way to do several things like signing, how to establish a secret between two peers. And what happened is that's in actually most Intel systems to date, right? And Windows 11 actually requires it. And it's traditionally used for UEFI, which is the boot, making sure that nobody's tampering with the boot process. And then also BitLocker, which Microsoft uses to protect all the passwords. And there's an older specific.
Sorry. Someone else just submitted a question saying the screen's not visible. It's visible to me. Can someone in the chat confirm if they can see the screen, the presentation? Okay, now it should be good. People are saying they can see it.
Okay, that's
sorry
really
about
that. Well, Zoom and issues with Zoom.
All right.
I had shared just the window, and who knows? I'll blame Zoom and Mac and everybody else in between. Sorry, guys.
All right.
So
Thank you.
I think we're good now. So, one of the things that happened, and one of the reasons we decided to write wolfTPM is because we had lots of customers, and they were embedded customers coming to us saying, hey, do you have a library that is, usable in the embedded space for a TPM? And so we ended up writing one from scratch. And what people were saying was that it was really complex. And if you look at the current stack of what it takes to use a TPM on something like Linux or Windows, there's many different layers, there's many different API interfaces. It's incredibly complex. Something that should be easy, it's incredibly complex. And so what we did was we said, we want no dependencies, right? So we wrote this library to be able to talk directly to the chip at the hardware level, on the SPI bus or the I2C bus. And later we added other interfaces, for systems that already have that transport layer, that TIS layer. So we implemented all of the APIs, the lowest level APIs, so the TPM2 APIs, and those are defined by TCG. Those are actually TCG defined 100%, what that API definition looks like and how it's used. So we implemented those first. And then what we did is we took all of the common use cases that people were asking us for, and we added wrappers on top of it to make it incredibly easy. And I'll go into more detail on this. But what the trends we're seeing are basically, safety critical systems where they might have a mandate to protect private keys. We're seeing a trend of people adopting a TPM, and there's a few reasons for it, which I'll go into. But like automotive, aerospace, medical, railway, and a bunch more, embedded IoT edge devices. And I think I have a slide on this, but the reason for it is there's a couple. So one is that the chip is designed, at least there's versions that are pin compatible from all the manufacturers, which I'll talk about. And that makes it easy to switch between vendors. It's also standardized, right? So the feature set that you get, the functionality you get is standard across all the TPMs. And if you compare that to something like a secure element that's dedicated maybe just for ECC, it's a very constrained set of features, and the SDKs and APIs for those change between chips. So in TPM 2.0, there's I guess I did talk about this, all the pin compatible chips. It supports RSA and ECC. You can do things like measured boot with the PCR, the platform configuration registers. Typically, these TPMs have larger non-volatile storage available, somewhere around 50K, sometimes more than that, over 100K, which is space that you could store anything that you really, really want protected, like keys, or I guess if you wanted certificates, but anything could be stored in these technically. They also have some really great one-way counters, and they have the ability to track time, which is pretty neat. There's support for encrypted sessions, so all of the sensitive data that's transmitted across the SPI or I2C bus, it can be encrypted if you do an encrypted session, and that uses AES counter mode, and there's also an HMAC for protection of the integrity. A lot of vendors, actually all of them have, I think all of them do, have a way to update the firmware in case there are issues that happen on the TPMs, which is really nice. Some of the vendors have even implemented some of the hash-based, basically quantum safe firmware updates. I've just heard about that. So standardized endorsement key, which means that these TPMs are actually manufactured with a pre-provisioned key and a certificate signed by the manufacturer. And that's part of the TCG specification. And then they have these really advanced policy management schemes that you can employ as well. So our library, it's the only stack that is designed for bare metal, no dependencies. There is no dependency on any sort of third-party library, anything at all. It's the only stack that can be used in a really small space-constrained embedded IoT device. For example, we support it within our wolf boot, in our secure bootloader, being able to do measured boot. And adding in our TPM library only adds several K. It's incredibly small. Yep, and we support any operating system. And we also have the C# wrappers that I mentioned. And that is a duplicate slide. And so we also have wrappers and examples for the common use cases I was talking about. So like key generation, loading a key, storing the key to NV, also creation of the primary keys, which are in the hierarchies, they're the root keys. The ability to do things like RSA, encrypt, decrypt, time verify, ECDSA, ECDH, all the non-volatile storage, HMAC hashing. And then we have examples for sealing and unsealing data, which is a way to actually protect a piece of information based on this, either a private key or the state of a PCR. You can do attestation, which is basically to attest to a certain piece of information, and you can sign it based on a key that's in the TPM. And then we support things like generating a certificate sign request, creation of a certificate that you could use with TLS, a bunch of great examples. It really simplifies, these common use cases. So these are the major TPM vendors that are out there: ST, Infineon, Microchip, Nations Tech, and Nuvoton. We support all these. We've tested with all of them. I have benchmark data on wolfTPM for all of these. And let's see, I don't know how much I can say about these. So those are the 5 major ones. They all have pin compatible parts available. This is a comparison I did a long time ago, and just compares some of the space, like non-volatile space. And I will admit this slide is a little outdated because Infineon has an SLB 9672, which has some newer algorithms and more space. These were some benchmarks I did also a while back for asymmetric algorithms. They're all pretty impressive, and they're all very comparable, to be honest. For an embedded device that's protecting your private key to be able to do that kind of those number of operations per second. So the higher number here is better. That's really, really impressive. So on our TPM library, we also have support for lots of different transports. So I mentioned we wrote around transport interface layer that's called TIS. So we have that, and we have that available if you're going to communicate directly with the SPI or I2C. But on systems like Linux, where you already have a TIS driver and you have maybe a dev TPM 0 interface, you can use that. On Windows, there's a TBS layer, which is an API interface layer for when you're on Windows and you want to talk to a TPM. And there's some differences there, but we've actually handled all those, and we have a C# wrapper too, which is really great. But one of the things is, from the TBS layer, you cannot store anything to the NV. You can generate keys, and you can get back the encrypted key. We call it key blob, but you can get that encrypted key data back, but you cannot store it on the TPM. But you can store it on the disk somewhere, and it's protected with a key that only the TPM knows how to decrypt. And then also we support the TPM simulator. We have instructions for that. So IBM has a really great software TPM simulator that we can run against, which is wonderful for testing. And then we have, SPI I2C interface support for Linux, Raspberry Pi, Windows, STM32, the Cube MX HAL, also the Atmel ASF SDK. And then Xilinx, we have drivers for. So we have customers using wolfboot with wolfTPM on a Xilinx chip. And there's also Bearbox support. Okay. And for building, it uses AutoComp configure. We also have some IDE examples for Visual Studio. And parameter encryption does require our wolfcrypt library for some key derivation, AES-CFB, and HMAC. We do have a small stack option. If you wanted to reduce the memory usage, it kind of reduces the buffers to the smallest, usable sizes. Our library is considerably less as far as code size and memory use. And we did a whole comparison on this blog post. So one of the engineers actually looked at our stack versus several other TPM stacks to show how much smaller it is. So, for APIs in our wrappers, there's a couple slides here that I like to go over that show a comparison of what it would normally take to do an API call for, let's say, a primary key generation, with the native APIs, the ones that TCG defined, and then the ones that we created, which are helper APIs. We call them wrappers. So, primary key generation of the native APIs takes about 49 lines of code. And, with our wrappers, it's like one API call, so it ends up being 5 lines of code. Same thing for like a normal key generation, so RSA or ECC key generation. This one would be the authorization. Yeah, so this would be if you were setting the authentication password for access to a key. So we have wrappers to help for that. Parameter encryption is a big one, and trying to do parameter encryption with the TPM start session, it's probably like 100 lines of code and some other things that are quite difficult. And, with us, it's just 10 lines of code to be able to do that. And parameter encryption is really great because it protects the first argument of each command, and it can either do that going to the TPM or from encrypt or decrypt. Yeah. Okay. So some real life examples, would be like a secure vault, key generation, protection of the long-term key used for TLS, attestation, measured boot. So like the secure vault example would be, to store any sort of private, public or symmetric key into the TPM's non-volatile storage. And you can associate a password with that for accessing it. And then you can use parameter encryption to protect it, the authorization, that password that's used. Another one would be key generation. So generating any type of key. Yeah, and you can generate keys that you can export, but the best feature of the TPM is be able to generate the private key on the TPM so that nobody can access it. Interestingly, the way that TPMs are designed is when you do create a private key, not a primary key, but a normal key, it does give you back that encrypted version of the key, and then you have to load it, and then you have to evict it, which is basically putting it into NV for permanent storage if you wanted to put it there. So for TLS, we have some really excellent TLS examples, all the way from doing a certificate signing request, creating a certificate that's usable with TLS, offloading all of the asymmetric, and if you want symmetric too, like SHA-256, all that can be offloaded. But most people just offload the asymmetric portion of it. So the ECC and RSA keys. You can even do the shared secret, so ECDHE. So you can have the TPM actually generate an ephemeral key, and then you can do that shared secret computation. That would be the key that's used for the session encryption during TLS. So attestation, you can generate reports from a TPM, and there's some different, there isn't really a standard for this attestation report per se, but the TPM is able to attest to the condition of something. It could be a PCR or some piece of information, like it could include a time. And we have some great examples for attestation in there in our library. So measured boot, it's basically a place so you can put a hash, and then later the application can go back and read that hash, and it can verify that the boot code that was used is what you expected, right? And that's very similar to what UEFI does in Windows. So I flew through this really fast. I do see a couple of questions. I'm happy to even do a demo. I wasn't really preparing one, but I could totally do a demo. But I'm open to suggestions. So, okay. Marcos, I see the questions. You want me to just read them off? And
yeah, if you want to go do that, that's fine.
yeah. So one of the questions is support for the older Infineon LPC bus, like the 9665. So we've been asked about it. I've put together at some point or another some example code for what that would look like, but it's not officially supported in our library. I think most of those older chips still use like the TPM 1.2 specification, and we wouldn't work with that anyways. If somebody wanted to help us, add the LPC bus support for a chip like that, and it was TPM 2.0, we'd be happy to help. Yeah. Another question is about post-quantum encryption. So it's a great question. The fact is that, with the post-quantum efforts, they're only now coming up with draft standards that they haven't even been released yet. And really, it's going to have to come through TCG, and it's going to have to come through the chip manufacturers, right? I have heard of, like I said just a little bit ago, that one of the chip manufacturers actually uses a stateful hash-based, post-quantum safe routine in their firmware update, but it's not something they expose, and it's not something that's available to us yet. Now in wolfCrypt, we do have support for all those post-quantum algorithms, and we're doing it right now through the liboqs library, which is open source library that standardizes the API interfaces for all the reference implementations of post-quantum. We've actually started our own implementation for Kyber. That'll be the first one. We'll have our own own code that we've written. That one we feel pretty confident about. So, and that's one of the key exchange algorithms that was selected in round 3. So, okay, let's see. I don't know this answer to this one, but the question is, any plans to embed the ARM assembly debugging and hardware acceleration commands. I don't know what you're referring to. So for the TPMs, I mean, we only have a very specific set of commands in the interface to the TPMs that we can support. Now, if we're talking about like C-level ARM debugging, yeah, that's a whole different topic. Feel free to add some more detail and I'll try to answer it. But so here's another question. Can you brief your TPM 2.0 synergies with NXP chipsets and microcontrollers? I think the question is around using the TPM 2.0 chips on an NXP microcontroller, I think. Yeah. So those NXP has a few different lines like the LPC and the Kinetis lines. To interface to that, we really just need a SPI driver. And the way we set it up is a single HAL callback. So you register one callback function for all commands and responses. And all you need to be able to do is send a command over SPI bus or I2C, depends on the chip, to the chip, right? And that is the extent of implementing new HAL support. We made it really easy. If somebody wanted to contribute some suggestions, we do accept code contributions to our GitHub, wolfTPM repository. Another question had to do with the OpenSSL. Oh, it disappeared. Hold on, I get it back. There was 2 questions in that one. So OpenSSL from Wolf compatibility with NXP. Well, I don't know how that applies to NXP, but our wolfcrypt library does have, and wolfSSL library has about 1,700 OpenSSL compatibility APIs. We have implemented support for using a TPM on the back end through our compatibility, but I'm not sure what that question is specifically asking. So this is a good question. How Wolf solution could be integrated with Linux native drivers? Yeah, so we have a build option that's -- enable dev TPM, and that makes use of the Linux kernel's TIS driver that's already exists, and so that's /dev TPM 0. So if you build wolfTPM with the enabled dev TPM, it will use the Linux kernel driver for all the commands, and all the APIs and everything on top of that maintain exactly the same. That's a great question. I think, as far as I understand it, from what I've experienced, our examples and the examples that you can build on top of the Linux ones, and their command sets, they're all interchangeable. Meaning you can use those at the same time. I'm not sure how the exclusive access is done with the mutex protection, but it does work. So another question is, what is the best solution for wolfSSL if we need only asymmetric algorithms for any bare metal embedded automotive project? I'm not sure how to answer that because it's not specific to a TPM, but if you're looking for asymmetric key protection like ECC and RSA and you're in bare metal and you have a TPM, I mean, this is a great solution, obviously. If you don't have a TPM, there's ways to get creative with how to protect private keys. And we're happy to have a discussion about it. You could always email facts, facts@wolfssl.com. Another question is, are all of your hardware solutions open source? So all of our solutions are software and all of it is open source. Everything is on GitHub, or you can download it from our website. So it's github.com/wolfSSL/wolfTPM for this project, this library that we're talking about. And everything is dual license. So we release it through GPL v2, but you can also purchase a commercial license if you wanted to use it in a commercial product. Oh, there's so many questions. Someone asked about secure element support. So with wolfTPM, we only support TPM 2.0 modules, but in wolfcrypt, there's a long list of secure elements that we do support. So like the @ECC or the ST-safe, or the, oh man, there's, like I said, there's a whole long list. The NXP has the SE050. I mean, there's several chips out there. Most of those do ECC. They'll let you create an ECC key. Most of those vendors have great ways to help provision. provision the chips during manufacturing. One thing to note is I did a webinar, it is on YouTube, and it compares basically secure elements and TPMs. I did it about a year ago. Some of the content similar here, but there was a lot that goes into a deeper dive for each chip that we do support on the secure element side. It's a really handy webinar. Yeah. Oh, yeah. Okay. I'm trying, I mean, there's a lot of questions here. I'm trying to decide which one to ask. So somebody asked on Linux, the kernel key ring control command. I'm not familiar with that. I would love to provide more info. And I'm just not familiar with that key ring control command, but, feel free to email us if you want to ask questions about how it might, relate to wolfTPM, or if that's a feature we should be looking at. This is a great question. So do you plan to offer a PKCS 11 provider interface for crypto operations that aren't specific to the TPM? That is a great question, a great suggestion. So one thing to note is that we in wolfCrypt, we do have a PKCS 11 interface, and we can either consume PKCS 11 or we can actually be a PKCS 11 provider. And we have all the pieces to do what's being asked there, which is, be able to have a PKCS 11 interface with a TPM on the back end, and things that aren't TPM based could use wolfCrypt. Absolutely. There probably just need to be a little bit of work to get it to all tie together. But our PKCS 11 provider interface is out there on our wolfSSL, GitHub repository, and it's pretty great. You should take a look at it. So another question here, as for older hardware without TPM 2.0, can one integrate an external TPM chip to existing hardware? Yes, you could. But you would, in that case, you would be adding a physical chip, but it would need to be over SPI or I2C bus. And you obviously could add it. And then there was any example on Linux that uses TPM 2.0 similar. Yeah, so that's what I'd use on my Mac. I use the IBM simulator, and we have, if you go to the wolfTPM library, there is a script that shows how to build and set that up. And then if you build with the enable, it's SWTPM, which is software TPM option, it'll actually use the 2 ports that the TPM server, the simulator, puts up. So they're TCP ports, and it will behave, our wolfTPM library and examples will behave exactly like it was talking to a real TPM, which is really, really handy for testing. I would happily show that as a demo. I don't know what time it is. We got 30 minutes, maybe. Somebody asked if the wolfTPM stack could be integrated into AutoZAR for automotive applications. We haven't done that yet, but it would be very easy to do that. If you look at the code base, I mean, it's not a significant amount of code. I mean, each of the code files is thousands of lines, and there's a couple of them, so it wouldn't be that difficult to do that. I mean, AutoZAR in general is really about coding standards more than anything. Sometimes they do define APIs, and I highly doubt they have APIs for that, but it's definitely possible. Okay, this is a good question. Did you look into the integration to ARM's PSA ecosystem for wolfTPM, especially with the Cortex M23, 32 versions, which are the ones with the trust zone? That is a super great question. It's something I haven't spent a lot of time thinking about, but in wolfCrypt, we do support using the PSA crypto APIs that ARM put together. I haven't thought about how you would necessarily integrate that with a trust zone on a Cortex, M33, let's say. But it would be very easy to do that. I'm happy to have that discussion. If that's something you want to talk about, I suggest you email us and we can set up a call. Somebody asked if all of the LPC TPM modules for, the TPM modules, the older ones that were TPM 1.2 were all LPC. And that's not true. Most of them were, but they did obviously have SPI versions of those as well. There may have even been one other bus variant, but LPC was really common at the beginning because of them being integrated into x86 systems. But eventually it shifted over to SPI bus. It's simpler. I think that's probably their main reason. Okay. I'm surprised that everybody's still here. Does anybody want to see the simulator demo? I wasn't really prepared to do it, but I can. So one of the things that we do is, so this right here, Ken Goldman from IBM, he put this simulator up, and it's pretty easy to build. You end up getting a file called TPM server, and you run it, and you can see it listening on here. I'm going to grow this. You can see it listening on a couple of ports, right? So that's step one. Build the TPM simulator and run it. The one thing to note is there's actually a file called nvchip here, and that file actually contains all of your NV memory, right? So if you create and store something on the simulator, it actually puts in that file, and you can actually just delete this file if you wanted to start over, right? Like imagine doing a TPM2 clear, and then we'll start this again. So next step is basically building wolfTPM with enable software TPM. I hope everybody can see this all right. Please let me know if you can. Yes, demo. Okay, well, as soon as it's done building, looks like my screen's a little big. So just to clarify, I did a configure. Oh, and I guess what I could do too is show you guys the GitHub wolfTPM page here. So this is our GitHub, page for it, and there's lots of great details here, including how to set it up and which chips and how to identify the device and build options. I think all the benchmarks are here. How to set up and use the TPM. Oh, and we do have CMake support. So then we do a make, and man, there's some, so you can always just test it with the wrapper test, which basically runs a bunch of, it basically does as much as you could imagine against, and the simulator reports as an IBM, which is pretty cool. So for TLS, there's a really great example, but the first thing you have to do is actually create and provision the certificates, which I've already done, but I'll go through it again. So in the examples directory, there is a README, and one of them tells you how to do the TLS steps. Yeah. So first we would generate like an RSA key. I did that wrong. And then we would generate the certificate signing request for that. Oh, I didn't build my wolf right. Yeah, I don't know. I guess I could go through this one. I think we should probably conclude the webinar before I go on too long. But as you can see, the simulator's there. And with configure help, you can see some of the other build options, right? So you can specify for, like this is the option for using the Windows TBS interface. This is if you're gonna, the dev TPMs, if you're gonna use the, somebody's asking if I could show an HMAC. So basically doing parameter encryption with HMAC. So all of our examples have, including, let's say the wrapper test, they all have help to do an AES, CTR, no, it's AES CFB parameter encryption. You just do -AES, and it's supposed to run out. It's because I don't have my wolf crypt built correctly. Oh, and actually, what we did is we made this really easy. So for wolf SSL, we can just do configure enable wolfTPM, and then we do make sudo make install. We can get past this. Yeah, so the parameter encryption is really cool because it's a way to actually protect and encrypt all the data as it's going across that SPY bus. So if somebody was passively listening on that, they couldn't actually identify the passwords that you're using, the key material that you were passing in, anything like that. So my Mac's being really slow. Marco, am I missing anything? Share the GitHub link. Yeah, so It's just GitHub/wolfSSL/wolfTPM. Okay, so now I built that. Build wolfTPM again. And now that I have our, wolfcrypt has AES-CFB, and in there I can do, well, I thought I could. Let's try one thing. Let's remove the NV chip. If I can type it right. And I guess it's been a while since I ran that one. Let's try the CSR again. So when you do a CSR, it generates the certificate signing request with some test data, and then we have a script that you can run to actually sign these. I remember where it is. And then you can end up running the TLS examples. So like TLS server demo. Yep. Well, I mean, if you guys really want me to keep going, I can, but I don't want to keep going too long here. So these steps are not memorized by myself, so I have to go to the README. We did the certificate signing. I do need to copy 2 certificates to TLS to the wolf SSL directory, and then I can run the server, and then I would run our example client. Oh, and I can actually do it with mutual auth right here. So then I would go back over here, and you can see that there was a successful connection. And if I have debugging turned on, you can actually see where it will use the TPM for the signing. Oh, and it looks like we do support parameter encryption here too. I was going to just build with debugging. Okay, this will be the last thing, and then we'll wrap it up. And I don't see any more questions. Marco, did I miss any?
No, there's a couple questions about the links, but I answered those.
Great. Yeah, I thought I put it in the chat there. Yeah, so with debugging on, you can see what happens. So as a TLS server, there's all these crypto callbacks. Most of them are not actually serviced, and we just return crypto callback unavailable, and it falls back to software crypto. But for the things we care about, like the RSA, the use of the RSA private key. Oh, I must not have set this up right. Yeah, still worked. I wasn't really prepared to do the demo, but we have really great documentation, and the demos do work when you follow the steps in the documentation. I think the TLS one is probably the funnest to do. You can actually turn on, so by default, it does the ephemeral key on the TPM, but you could turn it off to use software if you wanted to. Yeah, and I did mention, so there's a way to run benchmarks. So I did set up a benchmark tool with debugging on that. That doesn't look great. And it'll run benchmarks. And then there's another one for the clock. Is it time stamp? And there's one where you can generate assigned timestamp. Of course, this is not a real TPM, so maybe that's why the behavior is kind of odd and it didn't follow all the steps. But okay, let's conclude. Oh, can we have PKCS 11 to be used instead of PKCS 7? So I do have examples in here for PKCS 7. If any, and the answer is that there is no integration with PKCS 11 in the TPM yet. But us, wolfSSL as a company, we do have wolfcrypt has the ability to consume PKCS 11, and it also has the ability to be a PKCS 11 provider. PKCS 11 is kind of interesting because it's basically an HSM. So anybody who has like an HSM, they're using a PKCS 11 interface. We have this project, and this is a full-blown PKCS 11 provider that uses wolfCrypt under the hood. We've done some work to protect the private keys, like encrypt them, but it is relatively new. It's an interesting thing, and it would be fairly easy to tie this together with the TPM on the back end. And there's been some talks about doing it, but we haven't done that work yet. So, okay, I'm going to go ahead and wrap this webinar up. You guys have all been really great. Thanks for staying around and entertaining me with my demo shenanigans. So, hope you have a great day.
All right, just a quick reminder again. Yeah, if you guys have any questions, email fax@wolfcell. Also, if you want a copy of the slides, you can also email fax@wolfcell. But yeah, thank you everyone for your questions, and thank you, David, for the presentation. Enjoy the rest of the week.
Thanks.
Bye.